Hello everyone, and welcome to the latest MDPI webinar on energies, which is entitled Energy Production by Biomass Thermal Treatments. Thank you very much for joining us today. This is the first webinar of a series that is based in special issues and sections of our Energies journal. So please, if you are interested in submitting your manuscript to one of the special issues related to this journal, please check the webinar's website. Our chair today is Professor Fernando Rubiera from the Institute of Carbon Science and Technology in INCAR-CSIC in Spain. We will have three speakers: Dr. Covadonga Pevida from the INCAR-CSIC as well in Spain, Dr. Chungen Yin from Aalborg University in Denmark, and Dr. Ondřej Mašek from the UK Biochar Research Centre, University of Edinburgh in the UK. At the end of the session, we will hold a Q&A session, during which we will address all the questions submitted by live online audience. So if you're joining us live, please type your questions in the Q&A box and mention the name of the speaker together with your question. I would like to remind everyone that this webinar is being recorded and that we will post the recording soon in the webinar's webpage after the webinar has ended. Now I'd like to introduce our chair. Professor Fernando Rubiera obtained his PhD in chemistry from Oviedo University in 1991. With a Human Capital and Mobility grant from the European Union, he joined British Coal and then Nottingham University from 1992 to 1995. Then he started as a tenured scientist at the Institute of Carbon at the INCAR-CSIC, at the Institute of Carbon Science and Technology at the INCAR-CSIC, yes. He's currently a research professor and has been director of the INCAR since 2015. He also acts as a vice president of the Spanish technology platform, PTE-CO2, where he is in charge of the working groups for the capture and utilization of CO2. He's also the editor-in-chief of the bioenergy section of our Energies journal, and his research lines have included the reduction of sulfur dioxide and nitrogen oxides during coal combustion, the optimization of fine coal cleaning processes, the co-utilization of coal and biomass in combustion and gasification systems, the capture of CO2, and the catalytic production of hydrogen from biomass. So now I hand over the floor to our chair, Professor Fernando Rubiera, and to all of you. Enjoy the webinar.
Thank you, Elena. Thank you for your introduction. And good morning to everyone, or good afternoon, depending on where you are in the world, and welcome to this webinar. First of all, I would like to thank the journal Energies and MDPI for organizing this webinar, which is the first webinar series on energies. It's a real privilege to be with you all here today and for having the opportunity to interact with some wonderful and respected professionals. I just want to introduce our panel. We have Dr. Covadonga Pevida, we have Dr. Chungen Yin, and we are also joined by Dr. Ondřej Mašek. It's a real privilege, as I said, to welcome each of the panelists. Now, before going into the presentations, I'm going to present some slides. The first one, as I said, the journal Energies is part of the MDPI that this year celebrates its 25th anniversary. Energies is an open access journal, and the bioenergy section of the journal Energies is focused on regular and review papers related to all aspects of bioenergy production. Its scope is broad and includes the following general thematic areas like biomass treatment, biofuels production, generation of heat and power from biofuels, bioenergy and greenhouse gas emissions. You can find more information in this link. And in relation to this webinar, there are two special issues which are now open for the submission of papers. Dr. Pevida and myself are acting as guest editors of these two special issues. One of them is feature papers in bioenergy, and the other one is bioenergy reviews, open now for submissions. Now, the whole webinar is related to the energy production by biomass thermal treatments. Why we have selected this webinar and this title? Well, one is because biomass presents a series of advantages, such as CO2 life cycle neutrality, and this is related with the limit with the global warming. Also, in recent years, there has been a renewed interest in different biomass thermal treatment processes like torrefaction, pyrolysis, combustion, and gasification. Also, the different properties of biomass compared to coal have prompted the need to develop general models that address these differences. So in sum, this webinar will provide an overview of the thermochemical conversion of biomass, as well as advanced modeling efforts in biomass firing systems. Here you have the titles of my colleagues, of the presenters, and the format for the next hour. Elena has already said what we are going to do. Each of the three panelists will has a presentation, and I will turn over the microphone to each of them for about 20 minutes. Then we will go to the three presentations consecutively, and at the end of the webinar, we'll have some minutes for the Q&A section. If you have any question for the speakers, please post them in the Q&A box at the bottom of your screen. As Elena said, please remember to mention the name of the person you want to address your question. Now, I will introduce Dr. Covadonga Pevida. She is a research scientist at the Institute of Carbon Science and Technology in Spain. She is a chemical engineer and completed her PhD on the heterogeneous reduction of nitrogen oxides during coal combustion at Oviedo University in 2004. She was awarded the Young PhD Research Award from the Spanish Carbon Group in 2005. She undertook two postdoctoral stays at CNRS Université de Lyon and also at the University of Nottingham. In 2017, she was a visiting researcher at the Research Center for Carbon Solutions at Heriot-Watt University in Edinburgh. Her current research interests focus on biomass utilization for energy and value-added products, in particular, the production of hydrogen from renewable bioresources and the development of solid solvents for gas separation, CO2 capture. She has published more than 130 refereed journal papers with an H index of 50. She has been the head of the Department of Energy and Environment, and she is currently head of the Energy Processes and Emission Reduction Group at the Institute of Carbon Science and Technology. So I will hand out the microphone to Kova now.
Okay, good morning. For those of you who are in Europe, it is good morning, good afternoon, and welcome to this webinar. I first of all would like to thank you, Professor Rubiera, for the kind introduction, and of course the Energies Journal for inviting me today to be a speaker. So my presentation will focus on the biomass gasification and reforming with in situ CO2 capture. But during my presentation, I will give you an overall overview of biomass thermochemical conversion. And then by the end, I will show you some work, some research that we are doing within my group at INCAR-CSIC. So to start with, we need to clarify what we understand by biomass, because we do have a broad range of sources of biomass sources. So biomass is any organic material that derives for plants, animals, but this also includes not only agricultural or forest residues, but also municipal organic waste. But for those of us working on biomass, what is important is the use of biomass. So over the years, biomass have moved from a traditional use that was mainly focused on cooking and heating devices that were really inefficient and produce a lot of pollutants, to a more modern uses that involve the direct combustion to produce primary energy, and also the treatment of biomass so as to get more dense, energy dense materials for electricity and generation, sorry. But that is not the only biomass products that we can produce. We also have an increasing demand of biofuels, and of course we can produce biogas out of biomass. But what is clear today is that bioenergy accounts for about 70% of the global renewable energy supply, about the 10% of the total primary energy supply. And regarding the end uses of bioenergy, the largest share corresponds to the building sector with a 26%. So what is important of biomass, as Professor Rubiera has already highlighted, is that biomass takes part of the carbon cycle. So which means that biomass is produced by the photosynthesis and uses the CO2. So it's a natural contributor to the carbon cycle. But what is more important in terms of the energy utilization of biomass is that the CO2 emissions coming from biomass are considered neutral. So that is very interesting from the renewable and sustainable point of view. So we can end up with a summary of some energy pros and cons from biomass. If I need to highlight, I may say that biomass can be seen as a renewable, widely available, and diversified source of energy that can be cheap and that has a lot of potential in many applications. The main weaknesses could be that the large-scale devices may be costly today, that they may not have high efficiencies, and there are still some associated issues with environmental and health issues related to the use of biomass for energy production. But as I have already commented, there is a broad range of applications of biomass. So let's analyze a little bit the different pathways for conversion, product, and end use for biomass. We know that we do have a lot of feedstock possibilities, as I commented previously, but focusing on the production processes, we do have two main alternatives. One is the biological route, and the other one will be the thermochemical conversion route, which is the one that is we are focusing today. And within the thermochemical conversion, my presentation will focus on the pyrolysis and gasification. Moving to the product, the ranges of products out of biomass conversion, we also see that the range is very wide. But within my presentation, I will put the focus on biomass pellets, pyrolysis oil, synthetic gas, and biogas. Obviously, the main end uses of biomass products today are in three main blocks. That includes biofuels for transport, the combustion of biomass to produce electricity and heat, and biomass-based products. But my presentation today will also highlight the possibility of using biomass to produce renewable hydrogen. That you probably know is a very hot topic today. So to use biomass for energy purposes, it is important to pre-treat biomass because, as it was included in a previous slide, the density of biomass is low compared to the fossil fuels. So there are two main ways to increase the density. One is the pelletizing biomass. So you can pelletize biomass, and you see here how you manage to increase not only the bulk density, but also the energy density of raw biomass. But you can also treat thermal treated biomass in a process called torrefaction, that is a mild heat treatment, and you arrive with a significant increase in the energy density. If you end up by pelletizing this torrefied biomass, at the end, you will have a fuel with a very appealing characteristic to be burned in boilers. I'm not going into details, but just to mention that there was a statistical report issued last year in 2020 that you can check. It was issued by the bioenergy process and devoted to the pellets market. Focusing on the thermochemical conversion of biomass, that is the topic of the webinar today, you can see in the slide that the multiple pathways that you can follow in order to convert raw biomass into different products that go from heat, electricity, and chemicals. So we do have pyrolysis, liquefaction, that is today a hot topic, particularly the hydrothermal liquefaction processes, gasification and combustion. We can produce solid liquids and gases out of it, and also heat that then we can upgrade through different possibilities. And we end up with chemicals, fuels, and of course, electricity and heat, as I mentioned before. I'm not going into the details in all these processes, but I may suggest that you check a recent book by Energies that was published last year on biomass processing for biofuels, bioenergy, and chemicals. But before I move to the particularities of my talk today, I would like also to highlight that biomass conversion technologies are not at the same level of maturity. You can see that only on this side, you can see that only the technologies, the thermochemical conversion technologies associated to combustion to produce heat and electricity can be seen as a commercial today. We do have pyrolysis of biomass at, let's say, ready to market level, and we do have biomass gasification here. Biomass gasification is considered a demonstration technology today, even though the number of facilities has increased a lot. But you can see that one of the main drawbacks is related to the cost of the implementation. Obviously, these data are evolving, particularly in recent years. So I'm sure that this curve is getting low these days. So now I will focus on what I mentioned before. That was my main, what I intend to show you today is that by the thermochemical conversion of biomass, you can produce hydrogen. And you can produce renewable green hydrogen. So it is an alternative to what is commercial today for the production of renewable hydrogen, that is electrolysis. So the main pathways are to produce hydrogen out of biomass are summarized in the slide. So going through either pyrolysis or gasification, you will produce a bio-oil and a syngas after certain purifications that could then be reformed, and following the water gas shift reaction, you will end up with a gas that will have high concentration of hydrogen, but will also have CO2 that you may need to remove. So the key thing here, in order to implement the thermochemical conversion of biomass to hydrogen, will be the selection of the biomass feedstock that is more suitable to either the pyrolysis or the gasification route. Obviously, the development of catalysts is pivotal in the development of the technology, because they are needed for the reforming and water gas shift reactions. And of course, in order to get high purity hydrogen, you may need to remove CO2. So the separation technology that you choose to remove CO2 will be also critical in the development. But before moving into that, I will go into some generics related to biomass gasification. Gasification is very complex in terms of that it involves a lot of reaction that occurs at different temperatures. So you can see it as a summary of a drying at low temperature, followed by pyrolysis, where you will produce volatile matter, char, and a tar. that could then be further combusted and gasified. You can see in the picture the different zones that the biomass goes through in order to finally get your gas, and then obviously you will need to remove the ashes at the end. There are multiple types of gasifiers, and depending on the gasifier, the range of temperatures that you may be able to use will be different. Also, the type of feedstock is critical to decide which type of gasifier, and also there are limitations in terms of scaling of the gasifiers. I will not go into the details of the gasification technology because that is huge and there's been a lot of work on that. May I suggest two references for you in order to check more details? I would like to highlight here that depending on the gasifier, you will be able to handle, or you will limit it in terms of the capacity of biomass that you can handle. So when train flow gasifiers seem the ones with a higher capacity. Obviously, what is key in the biomass gasification process is the oxidation agent that you use. You can either use air, oxygen, or steam. Steam will be your choice if you intend to produce hydrogen. It is also important how the heat is provided to the process, if it is provided directly by the combustion of the biomass or indirectly. And also the pressure level, because gasification can proceed at atmospheric pressure, that is the most developed technology, or you can, or there are also the possibility of proceed at higher pressures. There has been issued a recent report by the International Energy Agency Bioenergy section that has summarized the wide and broad number of gasification installations in Europe. It's very interesting to check that. And it has to say that this number is increasing those days because gasification seems to be a very promising technology to exploit biomass. Obviously, when talking about biomass gasification, we cannot forget to mention the IGCC technology, which is the integrated gasification combined cycle technology. So gasification has the ability of providing not only a gas that can be further processed to produce hydrogen or to produce biofuels and chemicals, but there is also the possibility of using this producer gas in a gas turbine and in a vapor turbine in order to produce electricity. So that is what the IGCC technology is about. Moving into the reforming, that is also part of my presentation today, here we need to change the topic because when during gasification we can process solid biomass, for reforming, we need to pretreat this biomass. So we can reform liquid forms of biomass. When we aim at producing hydrogen, we will use water vapor as oxidizing agent. And there are multiple liquid derived biomass products that we can reform. That includes bio oil produced from pyrolysis of biomass. That includes glycerol, bioethanol. And also there's the possibility of reforming biogas. This is an interesting approach that we are doing research within my group, and I will show you later on. And that is because you can follow since biogas includes methane, you can reform methane to produce syngas that then you can move forward with the water gas shift to produce hydrogen. There are many facilities. I'm afraid there are small scale facilities that are producing bio oil for different, mostly to be further upgraded and used as a biofuel. But one of the largest one is located in Canada, as you can see in the slide in the picture, and you can see the scheme of how the RTI has developed this bio oil pyrolysis process. So moving into my topic today, as I mentioned before, if we intend to produce hydrogen out of biomass, we need to remove the CO2 that comes out of with it. So that links that with the concept of bioenergy with carbon capture and storage or utilization. This is known as the BCCS technologies or BCCU technologies. You can see in the slide the concept of these two technologies. It means that you are using biomass to produce bioenergy or biofuels. So in this process, you are producing CO2, and you can either choose to capture this CO2 and further use this CO2 for the production of chemicals, for instance. In this case, your process can be seen as net neutral, but there's also the option of storage the CO2 that you have captured, that is the BCCS concept, and is the only technology where you can really achieve negative carbon emissions. So that is very interesting when compared to the routes, the conventional CCS routes associated to fossil fuel. There has been a lot of not only research, but also investment on BECCS for different aspects. You can see in the slide some examples of facilities aiming at either BECCS or BECCU. The largest, the only one that can be considered the largest scale BECCS facility is this one in Illinois Industrial, that is run by Archer Daniel Midland. It processes up to 1 million tons of CO2 per year, and it is devoted to the bioethanol production by the fermentation of corn. So the CO2 that is captured is further storage in that case. There is a facility in Japan that can be considered the world's first application of CCU, so utilization of CO2 to waste to energy. It's been processing 3,000 tons of CO2 per year for crops and algae cultivation. And we also have BCCS in power generation. Another example in Japan, the Mirakawa power plant by Toshiba, that was a retrofitted power plant. It also has a CO2 capture pilot unit, but it was converted from coal to palm kernel shell power, and it is producing up to and capture up to 500 tons per CO2 per day. There are many other initiatives worldwide. Let me highlight the full small scale BCCU plants in US and Canada. The particularities of this installation is that they use the CO2 for enhanced oil recovery, some installations in Europe, and of course in Drax Power, which is a big example here in UK. But moving to my research experience, I will be focusing on the sorption enhanced processes with in situ CO2 capture. So first of all, what is relevant with this technology? Here, we are not separating CO2 once let's say as after being produced, but we are capturing CO2 during the process. So how it goes? It is like that. So for the assumption enhanced steam reforming, we've been using biogas, which has the particularity that we are not upgrading it, or bio-oil. If we combine the reforming reaction with the water shift and the use of a solid sorbent to capture CO2, we end up with high content of hydrogen in the gas stream as well as calcium carbonate. And the advantage of this technology is that the the thermodynamic says that it is slightly exothermic, which is huge, which is very good in terms of implementation. Within our group, we've been doing works with bio-oil components. So bio-oil is quite a tricky thing to work with because it is unstable, it's quite viscous, it has a quite high oxygen content. So we have started our research working with bio-oil components. Let me show you some of the outcome of our research. So on the left-hand side, you have the result of the sorption-enhanced steam reforming applied to acetic acid, acetone, and blends of those. What we have obtained after this research is a very high pure hydrogen at, let's say, moderate temperatures compared to other thermal processes. And what was very positive of the result is that we obtained similar hydrogen purities in the blends as in the individual components. Unfortunately, in terms of the hydrogen yield, they were a bit lower when we blend the two components. Another work we focus in running this sorption enhanced not only at atmospheric pressure, but also at high pressures. And we end up with the production of fuel cell grade hydrogen at both of them. Obviously, you can see that depending on the conditions, the range of temperatures that is optimum for high purity hydrogen production is different. And also, as I mentioned before, we are doing a lot of research in the use of biogas directly to produce hydrogen by biogas, by sorption enhanced biogas reforming. Let me show you the recent outcome of some of our projects. You can see in the slide both that by this sorption enhanced biogas reforming, we manage not only to produce very high purity hydrogen, but also at a high yield. And also we end up that the maximum hydrogen yield maybe was at temperatures a little bit higher than in the case of the bio-oil components, but it's still at temperatures that can be considered moderated temperatures. And which is important here is that the CO2 contained in the biogas that we are feeding to the system does not affect the performance of the whole process. We have also applied the sorption enhanced concept to steam gasification because we do have a background on steam gasification of biomass. There's a lot going on sorption enhanced steam gasification, but our approach here is a bit different to what you can see in the literature because we are also including a catalyst in the process, similarly to what we are doing for the steam reforming. So once again, combining the steam gasification of solid biomass, in this case with the water gasification reaction and the carbonation reaction, we end up with high purity hydrogen stream and also calcium carbonate. And also the process is slightly exothermic, which is very positive from an implementation point of view. Let me show you some of that results that we have obtained for two biomasses. Here you have torrefied pine sawdust and olive stone. You can see that in terms of proximate and elemental analysis, they do not differ much. However, when we test them for sorption enhanced steam gasification, we see differences, not only in the hydrogen yield, but also in the selectivity. As you can check in the slide, the dot points are for olive stones and torrefied pine. So you can see that here the yields are moderate compared to the reforming processes. So, but if we compare the sorption-enhanced steam gasification with conventional steam gasification, we see that in terms of hydrogen yield, we do not see such an improvement, maybe some improvement in terms of the cell activity. But what is important and needs to be highlighted is in terms of the hydrogen purity concentration with the sorption-enhanced steam gasification, we managed to obtain a high purity stream of hydrogen that we were unable to obtain with conventional steam gasification. So that was all from my side. I'm sorry that I take more time than anticipated. And thank you very much, everybody, for being connected today.
Okay, thank you. Thank you very much, Cova, for this nice presentation. Now we are moving to our second panelist, this Dr. Chungen Yin. I have known Chungen for about 10 years, and we have collaborated in several papers and presented some projects, but we don't know personally. This is the first time we meet each other. Hopefully in the near future, we will meet personally. Dr. Chungen Yin obtained his PhD in energy engineering from Zhejiang University in China in 1998. From 1998 to 2004, he worked at Zhejiang University as an assistant professor, then in École des Mines de Douai in France as a postdoc, and in Aalborg University in Denmark as an assistant professor. Since 2004, he has been an associate professor in Aalborg University. His research and teaching interests are mainly in the area of thermal fluids engineering. He has extensive R&D experience and competence in the thermochemical conversion of biomass for heat power and fuel production and related computational fluid dynamics modeling. He is among the world's 100,000 top scientists across all fields, according to the ranking of researchers carried out by the Stanford University, which assesses scientists for career long citation impact. So, Chungen, I am happy to give the word to you.
Yeah, thank you very much, Fernando, for your introduction and for your invitation. And yeah, hi everyone. Today I will give a short talk on modeling of biomass combustion and gasification. And yeah, for CFD, for modeling, it's so important in many areas in which fluid flow is involved. So for our area, for instance, biomass thermal treatment, biomass combustion gasification or pyrolysis. And I just want to highlight its role as mentioned in the big handbook, steam is a generation and use. Here, if you look at the last bullet point, I just copy and paste from this book, from the big, huge handbook. It says it's actually repeated for quite a few times in the book, throughout the book. New combustion system or design are often conceptually developed using CFD, followed by lab and site testing and adjustment or refinement. So for gasification and combustion, of course, if they are used as an independent technology, their purposes are very different. For gasification, as you know, it's mainly to produce combustible gases, syngas. And for combustion, the main purpose is to produce or to maximize the production of heat by completely burn out biomass into carbon dioxide and water vapor. And heat is the main purpose. And actually, gasification and combustion have a lot of similarities. Not only in the real life, they are actually part of each other. And if you look at commercial technologies, they are from both gasification and combustion. There are three major technologies. For instance, we have moving bed gasifier, and we have moving bed, or for example, we call grid boilers for combustion. For the second common technology is fluidized bed. We have fluidized bed gasifier, and we have fluidized bed combustor boilers. And also the majority is suspension flow, either gasifier or combustor boilers. So there are a lot of similarities between gasification and combustion. And since my focus is on the modeling point of view, if we say from modeling point of view, their similarities are even larger, even greater. And the major difference is of course, on the solid carbon conversion. In gasification, if we say we are now model simulate gasifier, we must retain the two reactions here at least. Solid carbon reacts with carbon dioxide with water vapor into carbon monoxide and hydrogen. That's basically the target reactions, target products. And if we are doing combustion simulation modeling, and of course we can still include the gasification, but the major reaction will be solid carbon into carbon dioxide and water vapor oxidizer. Oh, no, into carbon monoxide and carbon dioxide, depending on the reaction temperature, of course. So this is actually the major differences between gasification modeling and combustion modeling. So if you look at, we have three different technologies for both gasification and combustion. The first two include a kind of packed bed. For instance, for moving bed, fluidized bed reactor, we have a packed bed at the bottom of the reactor, or gasifier or combustor. So if we do the modeling of this kind of reactor, there are two separate modeling tasks. One is modeling the dense fuel bed at the bottom. And another is we need to do the simulation or modeling of the suspension flow chamber in a moving bed or fluidized bed. We call it a freeboard. And if we have a suspension firing boiler or gasifier, we don't have fuel bed. So this part, that top part, the suspension flow chamber is actually in common for all the reactors. So that's why we start. Of course, in the real life, the two different modeling tasks will be highly coupled to each other by the entrained combustible gases or combustion flow, which is released from the top surface of the dense fuel bed into the freeboard. And at the same time, by the radiation heat flux, which is emitted from the flame or from the hot wall in the freeboard onto the top surface of the fuel bed. Since the suspension flow chamber is in common in fluidized beds, grid boiler, and a suspension flow gasifier. So that's why, first of all, we focus on the suspension flow chamber or furnace gasifier, how to do the CFD simulation. So if you look at here it's a kind of very brief flow chart how to do CFD simulation of the suspension flow reactors. Basically, we have three major steps. The first step is to calculate the continuous phase flow field, of course, include a lot of equations, which means we need to calculate velocity, pressure, temperature, species, whatever, turbulence at the center point of each control volume in the whole reactor. And then the second step is to calculate the particle trajectory based on the continuous phase flow field. we need to update the trajectory, calculate the trajectory from the inlet until the particles leaves the computational domain. So along the particle trajectory, we need to update the particle fate because in this kind of topic, we have biomass reactions. So we need to update at each position along the trajectory. We need to update particle mass, particle temperature, particle composition, particle velocity. And then when a particle enters and leaves a control volume, we need to calculate a difference in the particle parameter. For example, particle mass difference, particle energy difference, particle momentum difference, and particle composition difference. These kind of differences will be used as an additional source term, which are produced by the particles onto the continuous phase. So that's why we have the last step. The third step is to update continuous phase source term, which are produced by the reacting particles. And then since we have a new source term in the corresponding continuous phase governing equations, of course, we need to recalculate the continuous phase flow field by updating temperature, velocity, pressure, turbulence, species of the continuous phase. And then we need to, based on the recalculated continuous phase parameters, we need to update the particle, recalculate the particle trajectory. So this is a kind of loop. So we need to do this kind of loop until both continuous phase and particle phase are converged. So that's basically a kind of flow chart, a very brief flow chart for modeling of suspension flow, no matter it's suspension flow, gas fire, or suspension flow combustor or combustion. So here, I just give you a kind of overview of different models when we do the suspension flow CFD or modeling. So at the center, we numerically solve the conservation equation of the flow field. Basically, we solve the continuity equation, Navier-Stokes equation, energy conservation equation, species conservation equation, everything. This kind of equation are rigorous conservation equations. There's no errors or uncertainty within this kind of conservation equations. And then this kind of conservation equations are supplemented or closed by a number of models. As you can see here, we have models which belong to combustion physics. For example, we need to calculate particle motion models, different forces, turbulence dispersion. We have turbulence models. As you know, we have turbulence is widely used in almost all the reactors because turbulence can enhance mixing, can enhance everything, of course. And we have radiation heat transfer. In combustor, in gas fire, we have high temperature environments. It's always radiation heat transfer that plays a dominating role in the heat transfer, mass transfer. So the three blue bubble is a kind of combustion physics area. And also we need to provide a number of combustion chemistry models to close this kind of modeling. So for instance, if we talk about biomass, of course, we have pyrolysis, mechanism, kinetics, whatever. And we have homogeneous reaction models. And of course, could be complicated depending on the problem. For combustion, for gasification, they are slightly different from each other, that's for sure. And as I mentioned, for char reaction, that's a major difference between gasification and combustion. For gasification, of course, char plus carbon dioxide, char plus water vapor, they are most wanted reactions. For combustion, it's mainly char oxidation into a mixture of carbon monoxide and carbon dioxide. So that's a kind of overview. Yeah, we have there are traditional models for this kind of for all the models, but I should say these kind of models have limited have their default applicability. For instance, they are used for traditional pulverized coal combustion. But now, if we have pulverized or milled biomass gasification or combustion, we have some special issues, which means we need to modify, we need to extend some of the models in order to make the entire scenario applicable to biomass gasification or biomass combustion. We have a number of specific issues need to be addressed in terms, in order to make the entire CFD framework applicable to biomass. So one is the first specific issue is biomass motion. So if you look at particle motion, normally, you know, we normally, the traditional model only solve the translational motion of the particles. And then we have this kind of equation of motion, and we have forces here, we have acceleration, we have forces per unit volume, per unit mass on the right-hand side. In the traditional model, we mainly retain drag force and gravity, which is applicable for this kind of particle, heavy, tiny, spherical particle, which is okay for the traditional pulverized core particle, which is on the order of tens of micrometers, nearly spherical and heavy, which means that density ratio, particle to air density ratio is about 1,000. But if you have a look at biomass particles, they are very different actually, depending on the milling process, depending on the preparation process. In the older day, a lot of biomass particles were prepared by direct milling of the raw biomass, raw straw, raw wood chips, so these kind of things, and produce quite large biomass particles. For instance, straw particles, wood chips. They are, if you look at the size, on the order of tens of millimeters, much larger than that. It's no longer a tiny particle, of course. If you look at their shape, they are far from being spherical or nearly spherical. And of course, recently in the past probably 10 years, yeah, we have this kind of process preparation method. Normally, the station power plant or gasification plant, what they received is not raw biomass. What they received is biomass pellets, and then they put the biomass pellet into the mirrors, roller mirrors, or whatever, different rollers, mirrors. So, of course, this kind of new preparation method results in somehow smaller particles. So if you look at the new method, normally we said we did a lot of measurement actually. The average size is between 700 or 900 microns, much larger, still much larger than this one. And the largest, the biggest could be up to 5 or 10 millimeters. If you look at their shape, they are still highly non-spherical. So if you look at the particles, the biomass particle has very different specific surface area characteristics. And this kind of characteristic will largely affect both motion and the conversion of the particles. So, and that's why we look into the first specific area, the motion pattern of the non-spherical, of the large, highly non-spherical biomass particles. So that's a kind of test we have done in the lab by mimicking biomass particles. It keeps the size, keeps the aspect ratio. And you can see nowadays, both translation motion and rotation motion is very important for this kind of large non-spherical particles. And then after that, we try to, we developed a model, try to reproducing our experimental study. And then we largely extend the traditional model, which is nowadays used for in the combustion or gasification community, modeling community. Nowadays, as I mentioned, the traditional model only solves the first equation, only solves this part, and with two forces in the equation of motion, drag force and gravity. And then we extend the modeling framework into translation motion and rotational motion. For the translational motion, we include a few more important forces: pressure gradient, virtual mass, especially lift force. And another thing is, in the equation of motion, we have drag force and lift force. Both the forces are dependent on shape effect of the particle and also particle orientation. So that's why we also need to solve the particle rotational motion. And then we have explained, and nowadays we have the torques, Tx prime, Ty prime, Tz prime. They are very complicated. We need to take into account all the important torques acting on the biomass particles. And another thing I need to highlight is the equation of the translational motion is described in the inertial coordinate system. And a particle rotational motion is described in the particle coordinate system. So that's why we need a kind of transformation matrix to bridge this equation and this equation. And a very complicated, that's for the particle trajectory, particle motion. And after all, the particle motion need to be coupled to the fluid calculation. So here I just pick up two figures for the results, which as a kind of demonstration show the validation in both translation and rotational aspect. So for the translation, you can see our model prediction agrees very well with our measurement. And for the rotation, the same story. We have a very good agreement between the particle orientation, the measurement, and the model prediction. So this is the first specific issue, which is very, very important. If you cannot calculate particle trajectory correctly, you can never expect we can trust the particle combustion or particle gasification, because the particle will be traveling throughout of the reactor. The second issue, as I mentioned, is particle conversion. So for suspension firing, one of the very important issues is we need to decide the maximum particle size that is acceptable for a certain pulverized fuel, either a gasifier or combustion, a boiler, to make sure we have a kind of complete conversion or complete burnout within the short residence time. Because we know for suspension reactor, the residence time of the particle in the reactive zone is very short, on the order of a few seconds. So that's why we did a lot of tests. For instance, in this movie, just to show this kind of wood particle. Size is 3 millimeters in diameter. And then about 10% moisture, 77 volatiles, 13 fixed carbon, and ash and negligible 0.3%. And then at a location of the particle, we have the gas condition well controlled. For this movie, it's 1,260 degrees C. The local oxygen 21%. So for this one, for this particle, we say after 6.5 seconds, it's burned out under this kind of condition. But still, as you can probably imagine intuitively, in the real life, the particle cannot, we don't have such a long residence time for the particle within the reacting atmosphere. And then we don't have 21% volatile, 21% oxygen everywhere in the furnace. So that's probably give us a kind of a hint. Okay, this if we directly inject this kind of particle in the real pulverized fuel boiler, most likely end up with high unburned char in the ash. And for this kind of large particles, for particle conversion, of course, we have conventional, we have traditional model, which is implemented by everybody, used by everybody in the commercial CFD. Of course, we have this. The traditional particle conversion model assumes a kind of sequential or step-by-step conversion pattern, which means for all the sub-process, heating and drying, devolatilization, and char reaction. This occurs step by step, which means devolatilization starts only after all the moistures are driven off from the particles. Char reaction starts only after all the volatiles are released. So that's kind of assumption or hypothesis behind the traditional particle conversion model. But now we have large particle on the whose size is on the order of millimeter level or even larger, 10 millimeter level. If you look at within the particles, we have actually quite a large temperature gradient. And as you know, all the reactions are very sensitive to temperature levels. So that's why in the real life, if we talk about large biomass particles, most likely we have this kind of simultaneous conversion pattern, which means all this kind of sub-process, heating and drying, devolatilization, char reactions, they do not happen step by step anymore. They actually occur at the same time simultaneously. So which means we need to refine the model. We need to develop a new model to somehow like replace the traditional model to make sure we have this kind of simultaneous conversion pattern. So this model, of course, is quite complicated. Again, if we look at the flow charts of this kind of model, of course, it includes a lot of blocks. Here, I need to highlight only 3 blocks or subroutine blocks. The first one is the particle interaction with the ambient flow. It's mainly to calculate the particle surface and the ambient flow heat and mass transfer. And the most important thing, or most difficult thing, is we need to solve the intra-particle conversion processes. We need to solve all the transport equations within the particles numerically. Mass, momentum, energy, reactions, everything within the particles. And the last key block is we need to update the particle overall parameters, for example, particle size, particle structure, particle as a whole. We need to update the particles. For example, we have a swirling, we have shrinking. We need to take into account this kind of thing into account. And then we developed a model, and we did, of course, a lot of testing for validation. For example, here we have this kind of particles, which is a real life particle we collected from the feeding line in the power station. It's hammer milled wood chips. The nominal size is 3 millimeters in diameter, but it's not a spherical. So we use camera size to produce a kind of comprehensive information of the particle size, a lot of things. And then for this kind of particle, we collect from the feeding line. And we did a lot of testing in the lab. For example, for these particles, we performed a combustion test under 3 times 4 different conditions, 12 different conditions, 4 different oxygen concentration, 5%, 10%, 15%, 20%, under 3 different temperature levels, 12,000, 1200, 14, and 1600 degrees Celsius. And then the major issue, of course, for the combustion test is to get the burnout time. And of course, we also try to reproduce this kind of combustion test by this model. And by this model, of course, we can predict everything. We can get a drying time, we can get a devolatilization time, and of course, we get burnout time also. And we compare with experimental study as a kind of cross validation of both our testing and validation. And then because later on, because for the power stations, it's not necessarily wood chips, there could be a different feedstock, could be straw pellets. So after that, we don't need to go for testing. We just rely on the model for different feedstock, for different particle size. We look into how quickly they can be burned out a typical sustained firing conditions, and then we can jump into some conclusion. Oh, do we need to adjust the mirror settings in order to produce the right particle size distribution, which is acceptable for this or for that boiler or gasifiers, suspension flow, of course. So that's basically for suspension flow reactor simulation for the overall and for the two specific issues for biomass application. And we have, of course, if we have moving bed or fluidized bed, we have additional, except besides the freeboard, besides suspension flow safety, as I mentioned, we still have additional efforts, additional model for the dense fuel bed at the bottom of the reactor. So basically to reproduce everything within the dense fuel bed. And then here, just to give you an example, of course, we also develop this kind of model, modeling of dense fuel bed conversion, not mainly for combustion application, but also can be easily reformulated into gasification or pyrolysis. So here, just to give you an example, I just show you the temperature profile on the left-hand side and the oxygen mass fraction on the right-hand side along that grade from the inlet, biomass inlet to the ash pit, ash outlet at a different heights above that grade. Just above the grade for one quarter of the height, bed height above the grade until the top. So when both the freeboard safety and fuel bed calculations are converged in a safety simulation of a real grid boiler. So just to kind of give you a kind of impression of the outcome of these kind of models. Actually, we have been involved in a lot of biomass plants, R&D, and even for the entire boiler, we have worked very intensely in a Danish power plant. You can see here, this is a kind of map of Denmark. We are located here, university. And we, even for the entire boiler, we have done at least 5 entire boiler. And also we have been involved in quite some local project, not entire boiler, but only looking to one single burner or combustor in some plants. So for the entire boiler, we have been involved in quite a few. Here are just some of the examples. For instance, 2 suspension firing boiler, the top 2, and the bottom 3 are grid firing boilers. So we have done a lot of comprehensive safety for different purposes for the power stations, troubleshooting, operation optimization, and also we develop a kind of new firing technologies, so-called spout firing, which is a kind of combination between suspension firing and grid firing. We have combined some of their characteristics or some of their advantages into one technology, so-called spout firing. And also, besides this kind of very comprehensive safety for the large boilers, we also develop a lot of new models. For instance, large biomass particle conversion, not only for combustion, but also for gasification pyrolysis. Biodroplet conversion, mainly for the large biodroplet evaporation, and deposit formation, which is a common problem in biomass furnace because of the low ash melting temperature, these kind of characteristics of biomass, and biomass fuel conversion, mainly for incineration combustion, and large non-spherical particle motion. And radiation, explain radiative properties on the different, on a new environments, for example, ox fuel, for example, ammonia combustion environments. They are very different from the traditional hydrocarbon combustion environment in terms of the radiative properties because we don't have, for example, carbon dioxide, or we have much more carbon dioxide. So that's why we need to, the radiative property will be largely changed. We need to develop new models. And turbulence, as I mentioned, we also develop turbulence modulation models. Yeah, the turbulence will affect the particle trajectory. On the other hand, the particle will attenuate or enhance fluid turbulence. So that's this area is not really well addressed, but we have spent some efforts. We did a lot of testing, and we try to come up with some models also. And also, we recently developed a so-called universal biomass pyrolysis model, which is quite different from the traditional model framework, Arrhenius model framework. And that's basically for modeling CFD. And nowadays, I guess everybody know, everybody talk about digitalization, and everybody talk about we will develop digital twin for this, for that. And I just look at some application or projects database. Even I found quite a hit this kind of so-called digital twin of, for example, gas fire, digital twin of a kind of combustor, or even digital twin of, I saw from the electrical guys, they say digital twin of a kind of converter. So which means modeling and CFD is becoming increasingly important in the future. We can basically use CFD or digitalization for everything, for every purpose, for all different areas. So if you need more details here, I just put some relevant articles we produced in the past 20 years. Somehow, like, if you need more details, basically you can find everything there. So that's it from my side. Thank you very much for your participation.
Thank you, Chungen, for your presentation. It's very extensive, and many people don't know the real utility of the modeling. So thank you for your presentation, Chungen. So we are moving now to the last presentation by Dr. Ondřej Mašek. The research of Dr. Mašek has been dedicated to various aspects of the thermochemical conversion of biomass and fossil resources to added value products. He joined the University of Edinburgh in 2009 and was a founder of the UK Biochar Research Centre at the School of Geosciences. His research has since then been focused on the conversion of biomass to biochar and co-products for the purpose of atmospheric carbon sequestration and adaptation to climate change. His research has expanded towards targeted biochar products, engineered biochar, and a more sophisticated method for biochar production and application. One outcome of this research has been the formation of a startup company called Carbogenics, which is focused on the development and production of biochar-based additives for the anaerobic digestion industry. Most recently, he started to work on the development of novel characterization and analysis methods for biochar and pyrolysis products with synchrotron-based 4D X-ray thermography. This work has produced novel insights into the internal structure of biomass and the changes it undergoes during heating. So please, over to you, Ondřej.
Thank you very much, Professor Rubiera. It's my pleasure to be here and to have the opportunity to talk about pyrolysis, and especially I'll focus on biochar, and to have the opportunity to talk to this the audience we have here, I assume from different parts of the world. So good morning or good afternoon to you, depending on where you are. My presentation will largely build on what we've heard in the earlier two presentations, so it's great I don't have to spend a lot of time on some of the fundamentals. Before I start on the topic of pyrolysis, I'll just briefly mention where I'm coming from. So as I already mentioned in the introduction, I'm based in Edinburgh. It's a beautiful city in the north of the UK, in Scotland, and specifically at the University of Edinburgh, where I've co-founded the UK Biochar Research Centre back in 2009. The centre focuses on different areas related to biochar production, development, and various areas of use. So my expertise is in the engineering, so it's the production technology for biochar, developing biochar as a material, and also its characterization. The center also investigates the various environmental applications, soil applications of biochar, as well as engineering applications. So we cover quite a wide range of areas there. We have a range of experimental facilities from small-scale laboratory instruments where we can work with milligram or gram scales of samples, all the way to pilot-scale facilities where we can test or scale up the production of biochar from laboratory all the way to pre-commercial scale, so at around 50 kilograms per hour of biomass throughput for our pilot-scale facility. So we can really do also field testing of the materials and larger scale tests with tens or hundreds or even hundreds of kilos or even tons of biochar. So moving on to the topic that I want to cover today, that's pyrolysis and how we can use it to produce or to valorize biomass. First, maybe useful, although we've heard a bit about it already, is to define what pyrolysis is, and to show you that all of you, no matter what your area of expertise is, you are actually familiar with pyrolysis already. So you can see here a schematic of a burning matchstick, as well as an animation of the process. And we are all familiar with the flame that we use for lighting candles and gas burners and so on. But pyrolysis is actually the process that's happening here where we don't see any flame. So it's on the boundary between the visible flame and the matchstick. It's in this zone where the charring happens. And what we have here is the heat coming from the radiation from the flame is heating up the biomass. It's releasing volatile compounds, and these are then the volatiles move into the air and then later on react with the oxygen, and that's where we have the combustion happening. But this area here where there is no oxygen present, that's where the pyrolysis occurs. So all of you have experienced pyrolysis many times in different ways. Pyrolysis is the process of thermal decomposition of biomass. It can be also coal. It doesn't have to be only biomass. When we heat it to temperatures of around 350 degrees and above. Before that, we have drying, so release of moisture from biomass at temperatures below 200 degrees. And in the zone between pyrolysis and drying, we have torrefaction. And that was already mentioned in the first presentation today as a method for pretreating biomass to make it more suitable for thermochemical conversion processes. And again, so pyrolysis is something we have all experienced, burning our toasts or chicken in the oven and so on. So that's sort of on the domestic front. It's also used quite extensively as an industrial process for management of waste, but also for conversion of biomass into various products. We've heard about bio-oil, so that's one type of pyrolysis. Now, pyrolysis process, although it's a very old process that's been around for a very long time, and there is evidence of pyrolysis being used for production of liquids and tars for various uses already hundreds and thousands of years ago, with industrial processes around already 100 years or more ago for production of liquids and chemicals that were used before crude oil was discovered as a good source of hydrocarbons. And the process sort of affects all the different levels or in terms of scales in the biomass. So starting from the microstructure, so the molecular structure, where the resulting products will depend, and the conversion process itself will depend on the composition of the material we are working with. So as most of you will know, biomass consists mainly of cellulose, hemicellulose, and lignin, as well as extractives and ash and other components. But these are the major building blocks of any biomass in different compositions and also different structures. So different type of plants will have different lignin and so on. And this very much affects the yields of the different products and the composition of the products of pyrolysis. So understanding the structure on the molecular scale is very important. Moving further up in the microstructure, so that's actually how the biomass material, how the solid biomass is built in terms of cell walls and how they are structured and how they are formed with capillaries and other parts of the structure. Again, this affects the process, and that's both in terms of the decomposition, but also the release of the decomposition products, how easily or they can escape the particles, how difficult it is. And then moving to the macrostructure, and we heard it in the previous presentation, depending on the size of the particle. So we can have fine, small particles. We can have large chips that are of very different shapes. So the macrostructure also affects then the heat transfer, the mass transfer, the flow of the material in different types of reactors, whether it's a moving bed or rotary kiln, and so on. So all these scales play an important role in our understanding and predicting what the composition of the final product is and what the yields of the products are. So yeah, here is a schematic showing that we have reactions going on here in the solid phase. We have the condensed phase as well as the gas phase, and all of these are happening at the same time. So making modeling of such a process very challenging if we want to go into all the details. So pyrolysis gives us three main co-products. We have the solids, that's the biochar, gases, and liquids. All of them have their different uses, and I'll go through those in the next few slides. There are different forms of pyrolysis or pyrolysis process that's put into different technological solutions. Here we have a diagram that shows some of the key thermochemical conversion processes, and we have a few types of pyrolysis here. So we have slow pyrolysis, fast pyrolysis, then there is a gasification here, microwave pyrolysis, as well as flash carbonization and hydrothermal carbonization. So all of these processes yield all three co-products, so the solids, liquid, and gases, in different ratios. Slow pyrolysis process, which is the process we are most interested in at the UK Biochar Research Center, is yielding among the highest yields of biochar, and that's why it's our preferred choice of technology. And it yields more or less equal amounts of the liquids, the solids, and the gases. So it's roughly 1/3, depending on the feedstock, depending on the processing conditions. Here, mainly, I'm referring to temperature, but as a rule of thumb, you can assume that it yields more or less equal amounts of those three. Fast pyrolysis, on the other hand, yields mostly liquid products, and it's optimized for that purpose. The aim of fast pyrolysis is to generate as much bio-oil as possible that can then be further upgraded or otherwise converted into fuels and chemicals. Gasification, as we heard, that's mainly focused on production of gas with a small amount of solid left behind. Microwave pyrolysis, utilizes a different mode of heating. So rather than using a direct heat transfer from a hot wall of a reactor or a hot gas, it uses microwave radiation to heat particles directly. As a result of that, the mode of heating is very different, and also the distribution of the products is quite different, and the properties of the products. And then we have the flash carbonization and hydrothermal carbonization technologies as well. So that's the different types of thermochemical conversion, all of which involve pyrolysis. Even gasification process has a pyrolysis zone involved there. It's just that after the pyrolysis zone, there is the gasification zone as well that decomposes the solids. So rather than leaving them behind as pyrolysis process would, it is gasified to produce more hydrogen and carbon monoxide. Pyrolysis technologies can be deployed on different scales and different levels of complexity. As I mentioned earlier, pyrolysis has been around for a very long time. It's been used for charcoal production since antiquity and perhaps even before. So it's a relatively well understood process on the surface of it, but as I mentioned, when it comes to the detail of the process, that is a different picture there. So charcoal production, very old technology. Now, there are newer approaches to charcoal production that are a bit more efficient, both in terms of labor and also the yield of the product. So you can see in the middle picture, that's a batch pyrolysis kiln. So it's a steel retort that's heated from the bottom. And when it's then opened, we have a char left behind inside, while all the gases and the vapors have been extracted and used either on-site or off-site. So this picture in the middle here, that's a charcoal factory in China. And finally, we can have it also in form of a sort of a real large-scale industrial process. This is an example from Japan, from Tokyo. And here they produce biochar in this particular plant. It's from sewage sludge, from wastewater treatment in a continuous process using a rotary kiln reactor, where the biomass comes in at the front end and the biochar comes at the back, and the product gases are used for heating the process itself. So it can be self-sustained. In case of sewage sludge, there is a need for additional heat input because of the high moisture content of the material. But for certain materials, the pyrolysis process can be self-sustained, and other than for the startup, it does not require further energy input. So looking at the uses of the different co-products, gases can be used either directly to be combusted at the production plant and used for heating the pyrolysis unit itself, with any additional heat, excess heat used for pre-drying of the biomass itself or for other uses. We can also clean the gas and use it in a combustion engine and generate electricity. So that's also a possibility, especially for larger plants where the gas cleaning equipment cost can be justified. Another option similar to the gases from gasification is to use to upgrade the gas and to use it for production of chemicals. That can be done either thermochemically in a Fischer-Tropsch process, where we can produce liquid biofuels, such as jet fuels and diesel and so on. Or it can be done biologically in a gas fermentation process that then produces ethanol, and this can then be further used for production of chemicals, or it can be used as a fuel directly as it is. So there are different options depending on the scale, depending on the complexity of the process, because of course any of these further upgradings mean more complex process. So the simplest option is to burn it on site, use the heat for running the process itself, and that can be done on a small unit on a farm scale or so. For large industrial applications, it will be one of the other options here that will be more suitable. For the liquid co-products of pyrolysis, we've heard about bio-oil. That's mainly coming from fast pyrolysis. From slow pyrolysis, the liquid is slightly different. It tends to be phase separated. So you can see here in this picture from our lab. So we have the aqueous fraction. So there's a light yellow fraction here, and the viscous tarry fraction, which is this dark brown liquid at the bottom of the flask. These have very different compositions. The aqueous fraction is mostly water with some lighter hydrocarbons in it, while the tarry fraction is mostly hydrocarbons and heavier hydrocarbons. Now, this can be further upgraded. This could be gasified to produce hydrogen, as we heard in the first presentation. We can extract various chemicals from it. The pyrolysis liquids are very complex in terms of their composition. We can also use this as a fuel directly, although with some restrictions there, it's not a great fuel before it's upgraded because of its acidity and high viscosity and so on. So upgrading is the preferred option here. We can also extract biologically active compounds from it that can be used as agrochemicals and so on. So there are a lot of different things that can be done with pyrolysis liquids. Just a few examples here. The composition of the liquids very much depends on the composition of the biomass we started with, but also on the processing conditions, whether that's the temperature, the heating rate, also the reaction atmosphere. We can do that under inert atmosphere, such as nitrogen or argon. We can do it under CO2. We can do pyrolysis under various different atmospheres, and that will all affect the resulting composition of the products. Here is a tank relevant diagram that perhaps shows the complexity even better, where each of the blobs on the diagram corresponds to a different compound. So there are thousands of compounds present in different concentrations in bio-oils, and we can see here on the right side, so schematically shown some of the key categories, and you can then associate it to where this sits on this graph here. We can then try to find ways how to extract these, perhaps how to use some of these as precursors for other chemicals. So there is, again, a lot of research potential there, a lot of application potential as well. Moving to the solid co-products, so the biochar, that has a number of uses as well. I'll show you a few examples of what biochar looks like, depending on what we start with. The picture I'm using here is a picture of what we call the standard biochar, which is a set of research-grade biochars we've developed at the UK Biochar Research Centre, and it's available for research to anyone who is interested in research with biochar. And you can see here, most of these are produced from pelleted biomass, so softwood, miscanthus, oilseed, rape straw, and wheat straw in form of pellets. We have granulated sewage sludge from water treatment and rice husk, sort of raw as delivered from a harvest. And you can see that the biochar tends to retain, when it comes from slow pyrolysis, tends to retain the shape of the starting feedstock, with perhaps some shrinkage occurring during the process, and also depending on the conditions. So you can see here samples produced at 550 degrees and samples produced at 700 degrees. As for the applications of biochar, here is a diagram that gives you some of the key categories, and within them some of the individual applications of biochar. You can see there are very many applications ranging from agricultural applications, environmental applications, various engineering applications, and so on. I won't have the time to go into any detail into any of these. If anyone is interested, I'm more than happy to discuss it either late after the presentation or offline. Here are the areas we are actively doing research in. So most of these areas, and there is really a lot of research that still needs to be done in many of these applications. One of the key reasons why biochar research has been initiated is the storage of carbon, or finding ways how we can store carbon that has been emitted to the atmosphere, how we can remove it and store it so that we can go back in time in terms of atmospheric greenhouse gas concentrations, or specifically CO2. So earlier we heard about bioenergy with CCS as a potential way how to remove, effectively remove carbon dioxide from the atmosphere. Biochar is a similar approach in that sense, together with a small number of other technologies. There really aren't that many technologies that can do that. In case of biochar, the way it works is that the carbon that has been removed by plants from atmosphere during photosynthesis and that's stored within the biomass, rather than allowing it to go back into atmosphere, so as part of the natural carbon cycle, we divert part of that carbon out of that cycle into a long-term storage. That storage can be either in soil, and that is a good destination for the carbon, because not only it stores it for a very long time, it also has additional benefits for the soil in terms of quality. So rather than just focusing on climate change mitigation, this can actually help also with climate change adaptation, because we improve the soils in terms of water retention, in terms of nutrient handling. So under changing climatic conditions, the soils can still maintain their performance at the same level, or perhaps even better when we use the right type of biochar. So really it's helping to solve two issues related to climate change, both the adaptation and mitigation. Storage can be also in various engineering and construction materials. It can be put back into where we've taken fossil carbon from, so disused coal mines and so on. So there are a lot of different options. The co-products, the liquid and the gas co-products of pyrolysis, can be used as a source of energy, so either for heating, electricity, and so on, as already discussed earlier. Just as an example of the potential for biochar and for pyrolysis technology in this regard, here is a very recently published paper that I contributed to in Nature Communications. And what this study has shown is the potential, specifically focusing on China as a very large emitter, but also a country with a large biomass potential. And what we have shown here is not only the carbon negative potential of biochar. So if you look at here, we can see that depending on the conditions we use in the process, the extent to which its net life cycle greenhouse gas emissions are negative, meaning sequestering carbon rather than emitting carbon to the atmosphere. So that can be affected by the choice of the operating process, but also the biomass. Besides the impact on directly on greenhouse gases, it also has impact on other environmental factors, such as emissions of various gases, such as SO2, NOx, particulate matter, and black carbon. And you can see here, or if you go to the paper, here you can read it in much more detail. The potential impact. So there is a lot of potential there for biochar, and this is specifically for China. You could extend that to sort of global impact. Now, in terms of the resources we can use for biochar production, it can utilize most types of biomass, whether it's a virgin biomass or non-virgin biomass. Virgin biomass has the benefits of known composition, a small amount of, or if any, contaminants. However, it has a higher cost and also a high competition with other uses. So, for example, there could be competition with food or competition with other uses. For example, timber for construction, or it can be for production of chemicals and so on. Then there is non-virgin biomass that has a lower cost but also there could be challenges associated with presence of contaminants. So that needs to be carefully considered and addressed in the process so that it does not negatively impact the resulting products from pyrolysis. And in the next few slides, I will go into present very briefly the potential integration of pyrolysis with other bioenergy technologies. And I'll have 4 examples here, and that's first-generation biofuels, second-generation biofuels, third-generation biofuels, and waste biorefineries. So starting with the first-generation biofuels, these rely on crops, mainly food crops, such as sugarcane and maize, to produce ethanol. And the ethanol can be either used for consumption by cars or people, and it leaves behind a large amount of residues. So depending on what biomass we are starting with, that can be corn ethanol, dry distillers grains, whiskey draff, if we are producing whiskey in Scotland, or sugarcane bagasse, for example, in Brazil, but also elsewhere. And these residues at the moment are often just combusted on site to produce steam or heat for the operating plants, or perhaps to produce some electricity in the boilers. This can, of course, be used for other processes as well. It can be used for gasification and produce other second-generation biofuels from thermochemical conversion. It can also be used for pyrolysis and again, generating liquids and gases that can be further utilized, and as well as carbon or biochar that can then be used back in the fields from which the biomass was harvested and help to close the nutrient cycle, and as well as store carbon, affecting the carbon footprint of those biofuels. Because as you are aware, different biofuels and also depending on different production systems have different carbon footprint, some of them better than others. And sometimes they face criticism for that. So putting some of the carbon back into the fields and storing it for a long time can improve that. Then we can move to second-generation biofuels. So that's a technology that relies on non-food biomass, such as lignocellulosic biomass, like trees or wood or straw and so on. And here we have an example of flow of carbon in a lignin cellulosic biorefinery, and you can see that the carbon goes into the different products, that's our chemicals and fuels, but most of it actually is left, so around 65% of the carbon is left behind in lignin and other residues from the process. Now, there is a lot of research going on the utilization of lignin in various different ways, but different type of lignins have different potential for further uses. So again, this could be a potential source of carbon for stabilization that could then impact again or improve the carbon footprint of such a biorefinery and its resulting products. So here we have different types of lignin coming from both either different biomass, but also different processes used in biorefineries. So we can have organosulf lignin, alkali lignin, kraft lignin, soda lime lignin. So these are referring to lignins obtained even from the same biomass, but using different extraction processes. And these can then be all used as a source for pyrolysis and for production of different added value products. Here I would like to mention a new Horizon 2020 project that we are participating in called Biomac. And if you are interested, please go to this website here. And the aim of the project is to develop new bio-based nanomaterials. And this includes work with lignin and nanomaterials produced from lignin. So our particular focus there is on carbon, but there are partners working on various different other applications as well. Just as an example of results for different types of lignin, you can see here that the yield of the solid carbon, so the biochar, is relatively high. So typically just under or above 50%, which when you compare it to typical biomass pyrolysis, you can see is considerably higher, sometimes double the yield. So lignin is a very good source of biochar or solid carbon. It also has very different properties than biochar obtained from raw biomass directly. Moving on to third generation biofuels. So here what I'm referring to is biofuels produced from algae. So here, because it's algae, it's an aquatic plant, it does not require land for its production. So there isn't a competition not only for food, but there is not even competition for land, which can sometimes be an issue even for second generation biofuels, where they may be taking over land that otherwise would be used for food production. So that is not an issue with algae. In this particular case, I'll be talking about macroalgae, so seaweed, that's available in different forms all around the world. And this has recognized potential to be a source of all sort of products, including very high value products such as food additives, but also pharmaceuticals and so on. Now, well, however, the extraction process for these high value products still leaves behind a large proportion of the starting material. So easily 40 to 50% is left as a solid residue. And this has a very low value. There isn't a lot of good use for that material. However, what makes it interesting for biochar production is the relatively high concentration of nutrients in form of minerals. So that can be potassium, it can be calcium, can be other minerals present there, also phosphorus, depending on where the biomass is coming from. So we can produce mineral-rich and nutrient-rich biochar from such products. There are some potential issues, of course, as well, such as presence of sodium. So again, there is a lot of development needed to overcome some of those issues, but it's a very promising material and with potentially very sustainable one. And finally, the waste biorefinery and integration of pyrolysis into that. So this here refers to waste biorefinery using anaerobic digestion. So this is a well-established technology with thousands of plants across the EU and several hundred plants in the UK using various organic residues. Here is an example of food waste, but it is also often used for processing of sewage sludge from water treatment plants, where the incoming organic material is decomposed, microbially decomposed, producing methane, or it can be also operated in a way that it reduces chemicals such as volatile fatty acids, and leaving behind the undigested residue, or the residue that could not be decomposed by microbes. That can be used directly on farms, but it faces a number of different challenges, most recently also related to presence of microplastics that come with the biomass source. So other solutions are being sought for this. And one of those is the potential of integrating with pyrolysis, where the solid residue is carbonized, turned into biochar, again with relatively high nutrient content because of the nature of the feedstock that's coming in. And this then has subsequent uses. There are a few different ways how to integrate this. So there are two-way synergies. There are actually probably more than two-way synergies here. So one is the use of the solid in pyrolysis. The other option is then use the liquid and actually feed it back into the anaerobic digestion process. And there are studies that have shown that this can be done effectively, and you can produce more methane and solve your problem with use of the liquids, especially suitable for small plants where you wouldn't invest in any upgrading process or so. Another option is to use the biochar back in the AD process as well, and that's an active area of research in our group. And it was mentioned in the introduction of spin-out company that Carbogenic has commercializing this as a product, so biochar-based product for improving methane yield in anaerobic digestion, and this is looking very promising. And finally, I'm moving to my last two slides. I wanted to just show you a concept that we have been developing under a EU project called Green Carbon that has just finished last month. And this is a sequential use of biochar or sequential biochar systems that is looking for synergies between different applications of biochar, so that each step in the sequence improves the properties of the biochar for the next use. So rather than producing biochar for one application, one target application, and that's it, which can be costly depending on the biomass we use, the conversion process, and so on. We can find ways to produce biochar, let's say, for gas absorption. After it has been used for that and it no longer is performing well enough, we can then use it for another application, for example, in anaerobic digestion or in composting or in water treatment and so on. And after that for another application or directly to soil. So we can have 2, 3, perhaps even 4 steps in the sequence. And each of the steps shares part of the cost of the production of the biochar. So overall, we can have a very economically attractive solutions in this way. So just a few points for conclusions. So the pyrolysis process can be used to process very wide range of biomass. It's really, especially slow pyrolysis, is very flexible in that regard. It can be configured in many different ways. So we heard about gasification, moving beds, fluidized bed, and so on. The same applies to pyrolysis. It can be operated in many different ways, and to suit really the type of biomass needed and the focus of on the products that we expect to have. And there are various synergies also between the pyrolysis, a thermochemical process, and biological conversion processes such as anaerobic digestion, but also gas fermentation. And there are various other benefits of the pyrolysis biochar systems, as shown on the example of the recently published paper. So environmental benefit, but also different societal benefits. So with that, I would like to thank you very much for your attention. I'm happy to take any questions.
Thank you very much, Ondřej, for your presentation. I think the first one is related with the part of the pelletization that Kova did mention in her talk. And the one is if forest residues are qualified for this process or only from tree logs. I mean, this is related with pelletization. Kova.
So yeah, I was wondering when I read the question, what was it related to? But of course, I mean, it's not only that they can be used, but is that they are the target to use waste rather than use other, let's say, biomass that could find other uses in, like wood for the wood industry or the paper industry. Of course it is. And we've done a lot of research on that, on producing pellets out of many different wastes and mixing them with lignocellulosic biomass as well. So yes, I mean, it's definitely a yes, and that is also a target, using waste.
Ondřej, you have also worked on this subject, no? Doing some pelletization with different residues, no? For example, it is quite difficult to pelletize torrefied material, isn't it?
Yes, yeah. So, well, we don't really specialize in the pelleting process itself. We work with pelleted materials, so we work with other colleagues who do the pelleting. We have done some work on pelleting of the biochar itself, because for some applications it's advantageous to have it present in a form of a particle that has a defined shape, such as a pellet or a granule. And yes, you're right that similar to torrefied materials, biochar itself, it can't be pelleted without use of some sort of a binder or an additive, because it's missing the lignin that would be normally used for binding together wood pellets and so on. So yes, there are challenges there.
There is another question that is directed to Cova. It's related with the fluidization of biomass together with calcium oxide. That this could affect the performance, but I also think that Chungen could say something about this related with the different sizes, the different densities of coal and biomass as well in FBC gasification. FB gasification. Because also COO, what do you use as bed material, Cova?
Well, related to the gasification bench pilot plant that we do have, we are using as bed material the ashes from a coal power station nearby. I know it sounds a bit strange, but it is, and it works. Regarding to the particular question by Marian, that I know she works a lot on fluidization. Obviously, we need to guarantee that we manage to get fluidization in the bed, because that is the key issue in the fluidized bed technology. We do care about the minimum fluidization velocity a lot. We do some calculations, but it's true that this is something we already, let's say, we do have background on that. So apart from these sort of calculations and managing with the particle size, that is important, which for us, what is, I'm particularly talking about the bench scale gasifier. For us, the tricky thing is to fit the biomass in there. Not all the biomasses are equally easy to fit in. So we have not performed a comprehensive analysis on the fluidization. We just take care and verify that the bed actually fluidize. Of course, when mixing the catalyst and the sorbent, that is something that could be more interesting to maybe to put some research on, but we haven't done it as yet.
You, Chungen?
Actually, we don't have a lot of experience in terms of the particle size for fluidization. Because in Denmark, basically, no matter gasification or combustion, it's almost exclusively based on suspension firing, a suspension flow reactor, or grate or moving bed reactor. There's little in the fluidized beds. But for the particle size, if you look at for the moving bed, for the grate boiler, they don't really care much about the particle size because it's acceptable for much wide particle size distribution. Its main issue is for a suspension reactor, because the huge problem in the beginning is because for the power station, they have fixed the user on the downstream side of the ash. So if they change from the fossil fuel to biomass without adjusting their mirror system, they have, in the beginning, they have huge problem in the very high unburned chair in the ash, which makes the downstream side very hard. They cannot accept the ash. So that's why they did, we also jointly did a lot of research in this area. For instance, for a given feedstock, the maximum or the preferred particle size for the suspension flow reactors. But we have very little experience, or we have done very little in terms of the fluidized beds or fluidization characteristics for particles.
Thanks, Chungen. Now I think I will do the last question for all of you. It's related with how do you envision the thermochemical conversion of biomass in the coming years, and related with this, the competition, or if it's an alternative to the green hydrogen production from wind, solar, electrolysis, or the green hydrogen produced from biomass. What do you think about it? Ondřej?
Okay, it's a very good question. So I definitely think that biomass has a role to play, but how it's going to compete, so specifically if we are focusing on the hydrogen production, the competitiveness between biomass and wind or other renewables that could be used for, so in case of wind, for electrolysis and production of hydrogen, that we will really see in the future. I mean, wind has been very successful. There's been a large and rapid deployment of wind. I can speak here in Scotland in particular. There is a lot of wind generation that has been built over the past 10 years, and plans for the future as well. So I wouldn't really want to guess how that's going to compare. I think where the future for biomass definitely lies is in various materials, so products such as chemicals, but also other products, so carbon-based products, because these can be offered by other renewable sources that can produce electricity or can perhaps produce hydrogen.
Okay, Chungen.
For biomass, at least in Denmark, or even in the entire Scandinavian countries, unfortunately, this kind of thing is fading away from the public funding. But still, I guess there's still some market, still some potential, because everybody talking about solar power, wind electricity is very good in Nordic countries, and they're trying to use surplus wind electricity or solar electricity for storage, sensible energy storage, or chemical energy storage, producing green hydrogen, green methanol, especially in Denmark or Nordic countries, and also green so-called ammonia. I guess the biomass still have a lot of good potential in terms of this kind of chemical production for fuels, for hydrogen, for even for chemical productions. But for at least for combustion part, it's fading away from the public funding. Unfortunately, we do not. We need to face it. Try to adjust our activities.
Mm-hmm.
Okay, Chungen. And Kova?
Yeah, well, I think it's quite complicated to give a definite answer, but obviously I see the potential. I work on that. And why I see the potential is, well, obviously, maybe with biomass, we will not compete for the large scale production of renewable hydrogen that we need for this, this structure, these hubs that are being ambitioned throughout worldwide, even, not even only in Europe. But we also need to think about other needs where for biofuels, we will need hydrogen. So it may be better to produce our renewable hydrogen out of waste that we could have locally and even by hand. So there is where I see a lot of potential for not, let's say, small applications where you do not have a distributed network where you can handle large scale production of hydrogen. So there, I think there is a big market there, and there are many possibilities in terms of technology development.
Thank you, Cova. And I think there is a last question. The question is from Jesus Rodriguez Reed. What are the most favorable operating conditions in pyrolysis to obtain a biochar suitable for the fabrication of electrodes, specifically to favor a good electrical conductivity?
Okay, very good question. So yes, that's a whole specific area of work for this type of electrodes, because there are different electrodes that biochar can be used for, including microbial fuel cells, and there the requirements will be different. But for this, usually the conditions used are what's used is a very low heating rate, so to minimize any formation of cracks or other faults within the carbon structure. As far as temperatures goes, usually higher temperatures mean higher conductivity. But what I would say is also very important to consider what starting material you are starting with. That I would say is equally important with the conditions. So very slow heating rate and very high temperatures as a rule of thumb.
With you again, Ondřej. Another question from Svelina Petrova. Is the pelletized biochar competitive with its final price? And what adhesives do you use to produce biochar pellets?
Okay, so good question. Yeah, so on my slides, I've shown a few examples of biochar. Most of them were pelleted. Just to clarify, those pellets were not produced after the charring process. These pellets, we used a pelleted feedstock, and it retained the shape of pellets. Of course, producing pellets from biochar is also possible, but then we need to use a binder. So it really depends on the purpose for which we want to use the pellets, because if you use a binder that then decomposes when you apply to the environment, so your biochar pellet breaks down, that may be beneficial, or it may be undesirable. So it really depends. But it's, I would say, easier to produce pellets first and then char it in a process. In terms of competitive for pricing, again, very much depends on the context. I would say, well, of course, the pelleting process adds additional cost. So it then depends on the value of the application. So you really need to have a good reason for why you want to pellet it. That can be because of the logistics of handling the biomass, just like for bioenergy purposes. And there are examples like Drax Power that was mentioned earlier that have a whole supply chain of pellets in very large quantities. And that's the economics of the scale really that makes it work. For small-scale biochar production, I don't think that would be necessarily a way to go unless there is a particular reason why you want to have a biochar in form of a pellet. So I think it's a bit of an evasive answer. There really isn't a single answer on that. I would say in most cases it won't be price competitive because of the additional need for a process and operating expenditure, but there will be examples where it does make sense because of the requirements of the product.
Thanks, Ondřej. Well, it has been a bit more than 2 hours that we have started this webinar. I think now is time to be closing the webinar. I hope all the audience have found the webinar interesting, and I think I have to thank all the speakers. And Elena, you would like to say anything else to close the webinar?
Yes, so before we go, I would like to thank you, Fernando, for chairing this session, and the 3 speakers, Covadonga, Chungen, and Ondřej, for your presentations and participating. I hope you enjoyed it, and I take care to all of you. Stay safe, and I think I will close now. So bye-bye. Goodbye.
Bye-bye.
Bye-bye.
Thank you, Elena.
Thank you very much.
Bye.
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 Thank you. Hi.
Bye.